Hello, and welcome back to my YouTube channel. My name is Professor Gavala, and today I will be talking to you about different analysis methods for circuits. This is the 8th installment lecture of the Circuits 1 series. If you haven't checked out the previous lectures, please make sure to do that because this lecture builds up based on the previous ones. Today we'll be talking about KVL, KCL, Nodal and Mesh Analysis, where we're just going to be doing these 5 examples or 6 examples, and I'll be explaining each of them and using these fundamental analysis methods. So to begin, we start off with this first one, and the first thing we want to do is we want to draw these loops called L1 and L2, and we want to write equations based on these loops. So for loop 1, let me zoom in here. I will write an equation as V1 plus 1 volt plus 5 volts is equals to 0. The way I get the minus and pluses in front of my values is from the way the current is entering the voltage source. So for the voltage. So for example, here L1 is entering V1 at the negative terminal. So I put a negative sign here. It's entering 1 volt at the positive terminal. So I put a positive 1 here. And it's entering the 5 volts at the positive terminal. So I put a positive here. Next, what I want to do is write an equation for loop 2. And again, I would say negative 5, again, because it's this current is entering this 5 volts at the negative terminal. It's entering this 2 volts at the positive terminal. So that's going to be plus 2 volts. And then it's entering V2 at the positive terminal. So this is going to be plus V2. And that's all equals to 0. Where this is my first equation and this is my second equation. If I wanted to solve for V1, I could then just say that V1 is equals to 6 volts. Or let me write that out explicitly. V1 is equals to 5 plus 1, which is 6 volts. And V2 is equals to 5 minus 2, which is equals to 3 volts. And what we'll say is that we'll put a note and say that this is KVL, or Kirchhoff voltage laws. And what we're doing here is solving for voltages. And lastly, this is the base point for what we call mesh current method or mesh analysis. Where if you remember from mesh analysis, which is in the previous lecture, lecture 7, please make sure to check that out. We're solving for voltages. So we write things like I1 times R1 plus I1 times R2, or plus I1 minus I2 times R3 is equals to 0, where this is a voltage 1, this is a voltage 2, and this is a voltage 3 equals to 0. So these are all, we're solving for voltages. So it's key to note that KVL is a fundamental principle or a base point when using things like mesh analysis method. So I hope that makes sense in terms of KVL. Now let's dive into KCL and realize this problem is asking us to solve for I1, I2, and I3. When we want to solve for I1, I2, and I3, we consider nodes. So we consider node A, node B, and node C. And we write equations based on the currents coming in and the currents leaving the nodes. Where if a current is coming into the node, like for example, I1 here, we consider it to be a negative current. But if the current is leaving the node, we consider it to be positive, a positive current. Where in most of your engineering classes, this is the convention that most, if not all, professors will use, and most, if not all, books will use. But sometimes, depending on how someone learned KCL, they might use the reverse convention where the current coming in is actually a positive current and the current leaving is a negative current. As a result, you might want to understand that using both methods will get you the same results. But in this lecture, in this example, for node, so at node A, I will use the convention where if a current is leaving the node, I consider it a plus. And if the current is entering the node, I consider it a minus. So in this case, 2 plus 12, because they're both leaving the node, minus I1 is equals to 0. And then at node B, we say I2 plus 14, because they're leaving the B node. And then minus 12 is equals to 0, because 12 is entering the B node. And then at node C, we have I3 plus 4, since they're both leaving, I3 is leaving and 4 amps is leaving, minus 14 amps, which is equals to 0. And I can come here and say that I1 is then equals to 12 plus 2, which is 14 amps. I2 is then equals to 12 minus 14, which is negative 2 amps. And I3 is equals to 14 minus 4, which is equals to 10 amps. As you can see, we're going to make a note, another note. And we're going to say this is KCL, or Kirchhoff current law. And in this situation, we are solving for currents. And we also say that this is the base point of nodal voltage method, or nodal, also called nodal analysis. And essentially, again, similar to this previous KVL, KCL is considered a base point or a fundamental analysis method for nodal analysis. And if you watch lecture 7, you would realize that we used to write equations such as Vx minus V1 over R1, where we're trying to solve for Vx, plus Vx minus V2 over R2, plus Vx minus V3 over R3 is equals to 0, where these are currents. This could be I1 plus I2 plus I3 is equals to 0. So I hope this makes sense in terms of KCL and KVL. So now let's go to the next example and maybe pause the video and see if you can solve it. It says use KVL to find V1 through V4. So in this problem, we're going to start off by doing our loops. So in KVL, they're called loop equations, where this is, we can call this L1, L2, L3, and L4. So in loop 1, we could say minus 3, because it's a minus, it's going into the negative terminal, plus V1, positive, minus V3, negative, is equals to 0. So this is my first equation. So loop 2, we could say minus V1, because this loop 2 is entering the negative terminal of V1 right here. So negative V1 minus V2 right here minus 2 volts is equals to 0, which is my second equation. Loop 3, we get positive 4 volts plus V3 right here plus V4 is equals to 0. This is 3. And loop 4, we get negative V4, positive 2 volts, and positive 5 volts is equals to 0, and that is 4. If we come and we could say here, we could solve for V4 is equals to 5 plus 2, which is equals to 7 volts. Then let's go to loop 3, and we could say V3 is equals to negative V4 minus 4 volts, which is negative 7 minus 4, which is equals to negative 11 volts. Oops, sorry. Yeah, which is equals to negative 11 volts. And then here, let's go up to the first loop, and we could say V1 is equals to 3 plus V3, which is equals to 3 minus 11, which is equals to negative 8 volts. And then here, we could say V2 is equals to negative V1 minus 2 volts, which is equals to negative 8 minus 2, which is equals to sorry, this should be positive 8 because it's negative 8 minus 2. So that's positive 8 minus 2, which is equals to 6 volts. So this is how you would use KVL. Again, we're solving for voltages to solve this problem here. So now let's go on to the next problem. Again, feel free to pause the video and try it out and see if you can get Vx here. But let's go ahead and do this. So we'll do our loop 1, since there's only one loop, and we'll call this I1. So we want to start here, and we say that this is a negative terminal. It's going into this negative 15 volt source, or it's going to this 15 volt voltage source, but we consider it negative 15 plus I1 times 1 ohm, or let's just say 1 times I1 plus 2 times Vx, again it's the positive, plus 5 times I1 because it's 5 ohms, plus 2 times I1 is equals to 0. The reason why we consider this positives here is because when a current is entering an element like a resistor, we consider that power is being dissipated, or there's a voltage drop in that component. So it's going from a positive, a higher potential to a lower potential. And the same thing here. So this would be plus, minus, and the same thing here, plus, minus. My current is going this direction, I1. Okay. And so that's why we say plus, plus, and plus here. Now what we can do is we can pull out that I1, so 15 volts plus 1 plus 5 plus 2, I1 plus 2 Vx is equals to 0. This here is 8 I1 plus 2 Vx, and there's a minus 15 volts here, is equals to 0. This is my first equation. And we note that Vx is equals to I1 times R Vx. And I1 is just I1. That's what we're trying to find. And RVx is 5 ohms, according to our equation right here. So we can plug this into here. And we get that this is our second equation. And we could say then that negative 15 plus 8 times I1 plus 2 times I1 times 5 is equals to 0. We can pull out an I1. We're left with 10 plus 8. This is 2 times 5 is 10 plus 8. And this is equals to 15. And then we could say I1 is equals to 15 over 18, right? 10 plus 8 is 18. We divide it over. So then this is equals to 5 over 6. And we know from equation 2 that I1 is, that Vx is equals to I1 times 5. So then Vx is 5 times 5 over 6, or 25 over 6, which is equals to 4.167 volts. So that's how you would find your Vx for this problem. And these are the steps you would take to solve for it. So I hope this makes sense. And now I'm going to go to the last problem here. And the last problem is asking us to solve for Vx and then also find the power absorbed by this 12 ohm resistor. Now keep in mind, what value or what will power absorbed be a positive or a negative? Maybe just answer that question and we'll come back to it. So to begin, we want to rewrite our circuit as an equivalent circuit. So we want to get rid of all this stuff. Okay? We want to call this R equivalent. In order to do that, I'm going to do it step by step. So, and this is practice from lecture 3, which we talked about resistance equivalence. So this here are 2 resistors in parallel, or 3 parallel 6, which is equals to 3 times 3 over, 3 times 6 over 3 plus 6, which is equals to 18 over 9, or equals to 2 ohms. This here is 8 parallel 12, which is equals to 4.8, using the same the same methodology. So now our equivalent circuit looks like, let me redraw it. Where this is 6 amps, this is 2 amps, this is 1 amp, this is 4 amp, this is 2 ohms, 2 ohms, this is 1.2 ohms, and this here is 4.8 ohms. We add these two in series, and when you add resistance in series, you say 4.8 plus 1.2 is equals to 6 ohms. And we also add these in series, so we get 4 plus 2, which is 6 ohms. So now, what I'm going to do is I'm going to erase this, and our new circuit is 1 ohm. This is 6 parallel 6, which is equals to 3. 1 second. Okay, let me draw it up nicely. So this is here. This is 6 amps. This is 2 ohms. This is 1 ohm. And this is that Vx we're looking for. And this is 3 ohms. And there's many different ways you can solve this circuit. You could say that you want to find Ix. And if you remember, Ix from our current division problem is the resistor that Ix is not flowing through. So this here is like Iy. So we take this resistance, so 2 over the resistance of the equivalent resistance of this resistor and these resistors here. So 1 plus 3 plus 2, and then multiply it by my current source, 6 amps, which is equals to, this would be 12 divided by 6, which is equals to 2 amps. And Vx is equals to Ix times 1 ohm, which is equals to 2 amps times 1 ohm, which is equals to 2 volts. So that's one way to solve for Vx. Another way to solve for Vx is if we use superposition here, which we learned in a previous lecture. You could say then that this is plus minus, this is 2 ohms, this is 1 ohm, this is 3 ohms, and this is 6 times 2 volts, or 8 volts, 12 volts. And what you can do is you can use a voltage divider here through this 1 ohm resistor. And the voltage divider says, so this is Vx. Vx is equals to the resistor drop, or the drop across the resistor that it's in series. So 1 over the equivalent resistance, so all these added up, which is 1 plus 2 plus 3, times my voltage source, this is equals to Vs, or times 12. Again, you get 12 divided by 6, which is equals to 2 volts. Another way you can do this is using nodal analysis. So essentially, if you remember from our previous lecture, if you had something like this, and this was that 6 amps, 2 ohms, 1 ohm, and 3 ohms. And this here is Vx. We could say Vx minus 0 over 2 ohms. So Vx minus 0 over 2 ohms plus Vx minus 0 over 4 ohms this is the 4 ohms here, Vx minus 0 over 4 ohms. And since this is entering the node, we consider this a minus 6 amps is equals to 0. We can say that Vx is equals to, let's actually do this. So 1 over 2 plus 1 over 4 is equals to 6. If I distribute this or make it an equivalent on the bottom, I would get 2 plus 4 over 2 times 4 is equals to 6. And then Vx is equals to 6 times 8 over 6. So that means Vx is equals to 8. So then I can find Ix. And we know that if Vx flows through this resistor, let me use a different color. If Vx flows through this resistor, it's also flowing through this resistors. So Vx is equals to, Ix. So this is Ix coming in here. Ix is equals to Vx over 1 plus 3, which is equals to 8 over 4, which is equals to 2 amps. And last but not least, I could then say that the voltage over the 1 ohm resistor is equals to Ix times 1, which is 2 times 1, which is 8. Which is 2 volts. Again, these are just showing you how to do it. This is nodal analysis. You get the same answer. This is essentially this is KVL, because I'm solving for voltages here. And here's this, and this here is KCL. So let's do the last part of this problem, which is the power across the 12 ohm resistor. And what I'll do is I'll redraw the circuit, but I'll do it in a simplified version of it. So this is here. So this is 6 amps. This is 2 amps. This is 1 amp. This is 6. This is 1.2. This is 4.8. Again, we get 1.2 by, or we get 2 by adding these resistors here. This is 2. And we get 4.8 by adding these resistors here. This is 4.8. So that's all we've done here. And we know that the current coming in here is 2 amps. And what we can say is this is I1 and this is I2. We could write an equation for I2 using our current division, which is equals to 6, so this resistor, okay, divided by 6 plus 1.2 plus 4.8 times this current, our source current, which is 2 amps, which is equals to 1 amp. Okay, another way you can see it is since this is also equals to 6 ohms, then that means that I2 splits between the 6 ohms and the 6 ohms here. So we get 0.5 Ix. Again, remember this is Ix, which is equals to 1 amp. So now, if we cancel this out, so this is 4.8, if we just cancel this out and consider that the voltage across here, this is 12, right? And rewrite the original problem of 12 and 8. So 12 and 8. We notice that the voltage drop across this, so this was before, it was 4.8. we notice that the voltage drop across here to here is also the same across this 12 ohm resistor. So what we can say is that V is equals to 1 amp, which we got from here, times 4.8 is equals to 4.8 volts. So that's the voltage drop across this 12 ohm resistor is 4.8 volts. So power across the 12 ohm resistor is V squared over R, which is 4.8 squared divided by 12, which is equals to 1.92 volts. And this is absorbed because it is positive. So again, this resistor does not supply power, it absorbs it. And we know that because it's positive. So I hope this makes sense in terms of all these problems and solutions. Let me know in the comment section if you want me to do more examples like this, and I will provide more examples. I will also try and do more shortened videos in my other project folder. So please make sure to check that out. It's called Electrical Engineering. And please let me know in the comment section if you have any questions. Please like, subscribe, and share my videos. Thank you. Have a wonderful day.